Am I au- am I audible? Okay. Good afternoon to all. Welcome to the 12th week and the last tutorial session of NPTEL course Thermal Engineering Basic and Applied. My name is Ananthakrishnan. I'm a PhD scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. So this week we'll be dealing with vapor compression refrigeration systems and gas turbine systems, thermodynamic analysis of both of them. We'll see a few numericals and multiple choice questions based on them. Looking at the first problem, it is regarding the vapor compression system. The refrigerated, I'll read through the problem. First problem, that is the refrigerated space must be maintained at -2 degrees Celsius to maintain that 240 kilowatt of heat is rejected by the condenser unit and 60 kilowatt of work is given to the compressor. Find the coefficient of performance of the refrigeration unit. So it's based on the vapor compression system. Try to solve this. I'll also try to solve it in a minute. Before going into the problem, we have to see what is the vapor compression system. Uh, System that we will be the thermodynamic cycle of the system. So it's a refrigeration cycle that takes in heat from a lower temperature zone and then delivers it to a high temperature zone, which works in a direction opposite to the nature's flow of temperature heat from a higher temperature to low temperature. So it shouldn't be violating the second law. For that, an external work needs to be done to take heat from a lower temperature site source and to deliver it to a higher temperature source. So higher temperature sink. So in this case, there's a condition space called an evaporator or a refrigerator space, which is at -2 degrees Celsius, which takes in heat from ambient temperature, which will be at a temperature higher than the evaporator temperature. Evaporator consists of heat exchanger, which consists of a refrigerant, which will be in a phase stage. Its temperature will be slightly its temperature will be slightly lower than its phase change temperature will be slightly lower than the ambient temperature. So ambient temperature in the sense the temperature in the conditioned space, and it exchanges heat, and the phase change material, the refrigerant moves from a liquid to the vapor system, and then from there it has to undergo a compression process, compressor, and then there will be a condenser which will exchange heat, which will reject the heat to the ambient. And then there will be a throttling valve that will be changing the uh, temperature as well as the pressure that will be bringing back to this evaporator inlet temperature. So in this process, the refrigerant will become vaporized in the evaporator. You can state it as 0.1, and from there, uh, external work needs to be done in the compressor to raise its temperature and pressure, and most probably the vapor will be in superheated condition, much above the freezing temperatures, and there will be a constant pressure heat rejection in the condenser where the vapor will be rejecting heat to the ambient and will be becoming a liquid, but it still will be in a high pressure condition. So in order to bring back to a low pressure, low temperature zone, we use a throttling valve or a capillary tube or an expansion valve, which is an isenthalpic process where the depending upon the refrigerant's Joule's coefficient, it will be reducing the temperature and the pressure. If you are to denote that, we have to demonstrate that on a TS curve. There will be a vapor dome, and the refrigerant will be undergoing phase change and will become vapor, and then there will be a compression. For the time being, we can take it to be an isentropic compression. Forget about the uh, irreversibilities in the process, and from there, it will be rejecting heat to the external condition in the condenser. That's also, and from there, and will be becoming a liquid. It can be subcooled liquid. For the time being, we take it to the saturated condition, and from there, there will be a throttling process that happens from 3 to 4, where the temperature and the pressure decreases. So the COP coefficient of performance is denoted as the heat input divided by work input for a refrigeration system. So heat input is not directly given, but we know that it's a cycle. So net heat input is equal to net work output. So we can denote that Q in plus Q in minus Q out is equal to, sorry, Q out minus Q in will be equal to the work input. So Q input will be equal to the work, the heat rejected in the case of condenser minus work input divided by work input. So it's given 240 and 60 will be 180 by 60, that is 3. And this is a surplus information which we do not require in this problem. So the answer is 3. It's a straightforward problem. for using the vapor compression system cycle. Look into the second problem. I'll also try to solve it in a minute. So look into the second problem. We have to find the refrigeration capacity. This is also a comparison. This is also a problem similar to that of the first one. So the enthalpy values at the end of compression process, evaporation process, and the condensation process is given. Condenser enthalpy of the refrigerant after exchanging heat in the condenser. You have to determine the refrigeration capacity if the mass flow rate of the refrigerant was found to be 0.5 kg per second. It's a straightforward one. So you can actually write it like this. We can draw the TS diagram. Uh, Isentropic process, compression, then this condensation in the condenser, throttling process, and evaporation process. So given H4 is equal to 60, H3 is equal to 260 kg per kilojoule per kilogram. H2 is equal to 180 kilojoule per kilogram. We have to determine the refrigeration capacity in terms of these two. So we need to determine 1 to 2. What will be the 1 to? So the process 4 to 1 is isenthalpic process. So H4 will be equal to H1 will be 60 kilojoule per kilogram. The refrigeration capacity could be written as the refrigeration effect into the mass flow rate of the refrigerant. So this will be equal to refrigeration effect will be equal to H1 minus H2. That will be H2 minus H1 into mass flow rate of the refrigerant. That will be equal to 180 minus 60 into 0.5. So this will be giving 120 into 0. So it will be 60 kilowatt. So answer is the first one. Straightforward one. Look into the third problem. The phenomena of a sudden drop in the temperature while passing the refrigerant through a capillary tube can be explained by a Carnot coefficient, Joule-Thomson coefficient of thermal expansion, and of the Joule-Thomson coefficient. So we have seen. So if the temperature and the pressure decreases, so that those refrigerants could be used in the case of a vapor compression system. Certain cases, the temperature increases when the pressure reduces. You can't use that. So that is given by using the Joule-Thomson coefficient. Look into the fourth problem. In a vapor compression cycle, the function of evaporator is to absorb heat from the outer space, reject heat to the surrounding, reject heat to the refrigerator space, absorb heat from the refrigerator space. So that option 4, we have already seen it. It will be absorbing heat from the refrigerator space. So straightforward. The lowest temperature in the vapor compression cycle occurs after the end of compression process, expansion process, condensation process, and none of the above. So we have seen in this previous problem, it is a particular point where the temperature will be the lowest. From there, it will be absorbing heat and it will be becoming vapor. Compression increases temperature and pressure, rejection heat, but it will be still at a higher temperature. Then there will be an isenthalpy process from 4 to 1. So basically, the point 1, which is just before the uh, evaporation process or the just before the evaporator or after the expansion process, that is where the temperature will be lowest. Look into the sixth problem. It's a problem on the gas turbines. It's a numerical. I'll also try to solve within 1 minute. So look into the sixth problem. A gas turbine operates on a pressure ratio of 6. The inlet air temperature to the compressor is 300 Kelvin, and the air entering the turbine is at a temperature of 577 degrees Celsius. If the volume flow rate of air entering the compressor is 240 meter cube per second, calculate the net power output of the cycle in megawatt. Also compute its efficiency. Assume that the cycle operates under ideal conditions. So it's a straightforward one. It's a gas turbine that operates on a Brayton cycle. We draw the TS diagram. There will be an isentropic compression of the gas followed by a constant pressure heat addition. Then an isentropic heat rejection, isentropic expansion, followed by constant pressure heat rejection. So we have to determine the efficiency of the cycle. We start from the values that are available. That is, inlet temperature is 300 Kelvin, and the maximum temperature is T3 after the heat addition, that is 577 degrees Celsius, that is 850 Kelvin. For an isentropic compression between 1 and 2, T2, we can use the standard reversible adiabatic isentropic equations. P raised to gamma minus 1 is a constant. We could be written in terms of the pressure ratio, that is T raised to gamma, P raised to 1 minus gamma is a constant. So P1 is equal to gamma minus 1 divided by gamma. So P2 by P1 is given as a pressure ratio of 6. T1 into 6 raised to gamma minus 1 divided by gamma. That will be 850. You can write gamma is equal to 1.4. We can assume it to be air. So it will be 1.4 minus 1.4 divided by 1.4. So it will be written as 6 raised to 0.4 divided by 1.4. It will be 509.18 Kelvin. Sorry, 5 zeros. This is not. Sorry. 500.81 Kelvin. Similarly, consider the isentropic expansion between 3 and 4. T4 could be written as T3 into P4 by P3, same compression ratio. That will be, we know the temperature, so it will be 6 raised to 0.286. That will be equal to 509.18 Kelvin. So we have determined that all the temperatures T1, T2, T3, T4. We can determine the work input to the system. So that is equal to work input to the compressor, that is constant pressure heat addition process Cp into T3 minus Cp into work input to the system. So that is isentropic process. Work input to the system. That is WC could be written as Cp into T2 minus T1. So it's equal to 1.005 201.81 kilojoule per kilogram. Similarly, work done by the turbine Cp into T3 minus T4 So it could be written as Cp into T3 minus T4, that is 1.005 into 850 minus 509.18 equal to 342.52. The reason why we could write these in terms of Cp into delta T is because this is basically the change in enthalpy, H2 minus H1, and this is equal to H3 minus H4 in the turbine. The work done or work input to a open system could be written in terms of the T3 enthalpy. So that could be for gas like an ideal gas, for an ideal gas like air, it could be written in terms of the change in the temperatures. Therefore, the net work could be written as Wt minus Wc is 342.5 and minus 201.8 equal to 140.72 kilojoule per kilogram. Heat input will be equal to Cp minus Cp into T3 minus T2. That is just substituting the temperatures. And we'll be getting the heat input as well. 350.94 kilojoule per kilogram. So we could write the efficiency equal to a net work divided by the heat input. That is 140.72 divided by 350.94. That is equal to 40.16%. So that is the efficiency part, and we also need to calculate the net power output of the cycle. So net this work is in terms of kilojoule per kilogram specific work. So in order to get the mass of the system, we have to use ideal gas. We know the volume flow rate of 240 meter cube. So if we know the specific volume or the density, we can actually get the value of the mass. So rho could be written as P by RT. Pressure at the inlet is 1 bar, R is 287 joule per kilogram Kelvin, and then temperature is 300. So you get the mass density of this one. Therefore, mass is equal to rho into volume flow rate, that is 1.161 into 240 meter cube per second. Then therefore, power input is equal to mass flow rate into net work. It's equal to rho into V into W. So here it is 1.161 into 240 into net worth is 140.72. So this gives the value 39210 kilowatt. So that will be the net. So that will be 39.2 megawatt. That will be the net power output of the cycle in megawatt. Straightforward problem. Look into another problem on gas turbine. It's also similar to the previous one, but it has got slightly more complication compared to the previous one. Look into it. I will also try to solve it. Okay. So the question is on a gas turbine cycle. It has a perfect heat exchanger. Air enters the compressor. At a temperature and pressure of 300 Kelvin and 1 bar and discharges at 475 Kelvin and 5 bar. The temperature of air the temperature of air entering and leaving the turbine is 870 degrees Celsius and 655 degrees Celsius. Assuming no pressure drop through the heat exchanger, compute the output per kg of air and the efficiency of the cycle and the work required to drive the compressor. So it's a straightforward problem. So before solving the problem, we can just put the state points on a TS plane. So 1 to 2 is a constant pressure, a constant isentropic compression. And for the time being, we can just denote this as 2 to 3 isentropic compression, 3 to 4 as isentropic expansion, and constant pressure heat rejection process. So here in this particular problem, there is a perfect heat exchanger that uh, transfers a bit of heat from the expanded gas after the expansion to the gas which is slightly compressed. So in this particular process, it's kind of a regeneration uh, where a portion of the exhaust gas heat will be used for heating the uh, for improving the efficiency. So a portion of that will be taken care will be used to preheat the air. So in this process, the perfect heat exchanger. So it takes a heat and becomes 5. It rejects a heat and become uh, 0.6. So in this problem, first part, output per kg of air. So this is work net equal to work done by the turbine minus work input to the compressor. Work done by the turbine is equal to the same change in enthalpy Cp into T3 minus T4. That is 1.005 into 870. This temperature is 870 T3. And leaves at 655. So the net work, the work is 216.07 kilojoule per kilogram. The compressor work, that is Cp into T2 minus T1. This is isentropic compression process. So that is 1.005 temperature. It's given in the problem. 475 minus 300. So that is equal to 175.9 kilojoule per kilogram. So this is the solution to question the part 3 of the problem. So the net work will be equal to work produced by the turbine minus work in the compressor. That is now the going to the efficiency. For that we need to calculate the heat input. The heat input equal to Cp into T3 minus T5. I need to it will not be from starting from 2 because a portion of the total heat input will be taken care by the preheater. So that will be equal to Cp into T3 minus T5. This 1.005 into 870 minus 655. That is 216.07 kilojoule per kilogram. Efficiency is straightforward. That is net work work net divided by heat input. That is 40.175 divided by 216.07. It is 18.5%. If you compare this between to other cycle like auto and the diesel cycle, this efficiency is very low. But it operates at a higher temperature. Look into question 8. This is also on gas turbine. Small increment. So we are actually going through small increments between from one problem to the other, changing a few parameters and trying to solve the efficiency in almost all the cases. Look into it. I'll also try to solve it in a minute. So it's a gas turbine unit that operates at a mass flow rate of 30 kilogram per second. Air enters the compressor at a pressure of 1 bar and temperature of 15 degrees Celsius, and is discharged from the compressor at a pressure of 10.5 bars. Combustion occurs at a constant pressure and results in a temperature rise of 420 Kelvin. If the flow leaves the turbine at a pressure of 1.2 bar, determine the net power output from the unit and also thermal efficiency. Take Cp equal to 1.005 kilojoule per kilogram Kelvin and gamma equal to 1.4. So in this particular problem, combustion occurs at a constant pressure, results in a temperature of 420 degrees, 420 Kelvin. Temperature rise. If the flow leaves through the turbine at a pressure of 1.2 bar, uh, determine the net power output from the unit and also the thermal efficiency. So it's slightly more trickier compared to the previous problem. If I try to plot this in a TS plane, one to two isentropic compression, heat input, uh, isentropic expansion process, then heat rejection. On compressor, work and turbine. So given temperature, input temperature is 288 Kelvin, and the pressure ratio P2 by P1 equal to 10.5. Basically 10.5 by 1, 10.5. So 1 to 2, it's isentropic compression process. At the end, we have to determine the net power output from the cycle as well as the thermal efficiency, just like the previous case. So here T2 is equal to T1 into P2 by P1 raised to gamma minus 1 divided by gamma. So that will be 288 point into 10.5 is 564.22 Kelvin. T3 is equal to T2 plus 420 rise in temperature during the heat input process. So that is 984.2 Kelvin. T4 will be equal to T3 divided by T3 by P4 raised to gamma minus 1 divided by gamma. So that is 984.22 divided by 10.5 by 1.2. So P4 is not equal to P1, it is different pressures. So 1.2 raised to 0.286. So that is 529.27 Kelvin. Therefore, water in the compressor will be equal to m dot Cp into T2 minus T1. So that is mass flow rate into 1.005 into 564.22 minus 288. That is equal to 8328 kilowatt. So we got the work input to the compressor. Now work output from the turbine. So m dot Cp into T3 minus T4. Same analysis. So you know the mass Cp. It's basically changing enthalpy. We could write in terms of temperatures and Cp. So that is 13716.74 kilowatt. Therefore, work net is equal to Wt minus Wc. That is 5388.74 kilowatt. Heat input could be written as m dot Cp into T3 minus T2. So it's basically these process that is equal to 30 into 1.005 into 40. It's a constant pressure process, right? So if you try the heat transfer, heat change into the heat input would be written in terms of change in enthalpy. Therefore, thermal efficiency is equal to work done divided by heat input. So this is also this was also a similar problem compared to the first one, but here the only difference was that the temperature rise was given straight away. So we could actually correlate it and get the we could actually correlate straight away to get the heat input. The network could be represented in terms of the turbine work minus compressor work, and thermal efficiency was straightforward. Look into the final problem of this session. This is slightly different from what we have seen till now. I'll give you a minute to look into it and then I'll also try to solve it. So the question is on a centrifugal compressor under test gave the following data. Speed is 11,500 revolution per minute. Inlet total head is head temperature is 21 degrees Celsius. Outlet and inlet total head pressure is 4 bar, 4 bar and 1 bar. Impeller diameter is 75 centimeter. If the slip factor is 9.92, what is the compressor efficiency? It's a slightly different problem from what we have seen. It's a problem on a centrifugal compressor. Its speed is given in terms of RPM. Inlet total head temperature is given. Outlet and inlet pressures are given. Impeller diameter is given. We need to calculate the compressor efficiency. So we can try to plot it in a TS diagram. How does this compressor look like? The the point looks like. The process looks like. So if it was an isentropic process, it would have looked like 1 to 2, 1 to 2 dash. But the actual process will be slightly curved towards the right to take into account the slips as well as the irreversibilities. The efficiency could be written as ideal enthalpy change in the compression process to the actual enthalpy change. That is T02 dash minus T01. This is one. T2 dash to T1 divided by T2 minus T1. So basically this actually is not the static temperature. You have to take into account the total inlet head temperatures. So that's why I had initially written as T03. So you have to take into account the the total inlet total head temperature. So that will give T01. At the inlet, it will be same. T01 will be same as T1 is equal to 294 Kelvin. But then we have to determine the temperatures T02 as well as T02 hash. So we can try to solve it in a different manner. So we can calculate T02 hash. It's an isentropic process. So we know T01, T02, T01 gamma minus 1 divided by gamma. So the outlet and inlet total head and pressure. Head pressure is 4 and 1 bar. So from this one, we can directly get 4 raised to gamma minus 1, 0.286. That is equal to 437 Kelvin. So we have got this value for the ideal part, but in order to get the actual one, we have to take into account the slip factors and the final actual temperatures. We can get it from the compression work. So compressor work will be equal to the actual compressor work will be equal to Cp into T02 minus T01. That could be written as this could be written as the slip factor into the velocity squared. So slip factor, it's actually a coefficient that corresponds to velocity squared to the actual work. So this could be 0.92 into pi into diameter 0.75 into 11,500 divided by 60 the whole square. That will be equal to 187.63 kilojoule per kilogram. So equating these and this, we'll get the value of T02 equal to T01, that is 294 plus 187.63 divided by 1.005. It gives 480.7. So that gives the temperature T02. From this, the compressor efficiency could be written as T02 minus T02, T02 minus T01 is 437 minus 294 divided by 480.7 minus 294. That equal to 76.6%. It's a straightforward problem where we have used the total head temperatures at the inlet and the exit, to calculate and compare it with the isentropic temperatures to get the compressor efficiency. That completes the set of problem that I have for this week, and that is the end of these tutorial sessions. Before winding up, we'll just go through what we have seen in the previous 12 weeks lectures. We have initially done a few review of the thermodynamics in the first week. Then we had gone into steam turbine, steam power engineering, the steam power plants, Rankine cycle, modified Rankine cycles, different reheat, regeneration, superheat cycles from week 2 to week 2 to 4. Then we have seen a few problems on second law analysis of the steam power plant. Then in the fifth week, then we have moved into individual parts of this power plant. We have seen the boilers in the steam turbines and the flow through the nozzles. Then after that, we had moved into the velocity triangles for the turbine, steam turbine parts, and finally to the condenser. And the last one was the cooling tower analysis. So from there, we had actually moved into internal combustion engines in the week 10. And we have seen SA and CA engines performances. And finally, in this week, we have seen refrigeration and gas turbine cycles. So if you have any doubts, we can post it in the course website forum. That's all. Thank you.